Hi, today's lesson is going to be a basic introduction to motion. I'm going to define various terms for you as well as give you some visuals to help you understand them. So let's just start with the simple x, y, z coordinate system. When trying to find the position of something, we'll typically use something that you'd find in, say, a math class. So we have our x-axis, where right we would define as positive x, left would be negative x, up would be positive y, and down would be negative y. The z direction would be, like if you're looking at your monitor, if you came out of your monitor towards you, we'd call that the positive z direction. If you go back behind your monitor, we'd call that the negative z direction. So when trying to figure out our position, you're looking for some absolute location. So for example, let's say I'm located right here. So I'm 4 meters to the right of, say, our origin here, 4 meters to the right. So we'd say, okay, we're +4 in the x direction, and we're 2 meters below the origin. So we would say we're -2 meters in the y direction. And then if we're on a two-dimensional screen like this, we'd then be 0 in the z direction. So you can kind of use this to find where our absolute location or position is anywhere on the screen, or if we come out of the screen, we'd be in our positive or negative z direction. Now in this class, we're typically going to just use a two dimensions, x's and y's. So we also often use east, west, north, south, kind of our compass system as well, where plus x would be east, to the left or negative x would be west, and up would be north, plus y, and down would be south, negative y. Okay, so let's keep going. Position, again, like I said, this would be our absolute location with respect to some system that we defined. Our distance, so this distance essentially means how far something travels in total. So for example, if you walked to the store, you might say I traveled 1,000 meters to the store. And if you walk back home, then you might have traveled 1,000 meters to the store and 1,000 meters home. So you traveled a total of 2,000 meters distance. The symbol we're going to use here is d, and the unit we're going to use is meters. Now displacement, on the other hand, is our change in position. So how far we are from where we started. So for example, with the store, if I walked to the store, I might have walked 1,000 meters. Well, my displacement would have also been 1,000 meters because I'm 1,000 meters from where I started, but we're going to include our direction here. So I might say I'm 1,000 meters to the west from where I started, and that would be my displacement, 1,000 meters. Now if I walk back home, I go 1,000 meters, then 1,000 meters back home. This would be 2,000 meters distance that I travel. However, my displacement would be 0 because I'm 0 meters from where I started. I started at home and I ended at home, so that's 0 meters. The symbol we use, since we are talking about a change, we're going to be using delta D. You'll also see delta X, delta Y, or delta Z if we're specifically talking about one dimension. But I'll often just use delta D for kind of a generic how far I am from where I started. The units, if you notice, are the same. You're just going to make sure you include direction here. I'm going to go ahead and give you a few examples of this just to give you a better visual. So let's take a look at the differences between these three terms. So let's say, for example, I start here at 0. Let's say I were to move this way to the house, 8 meters. Now we would say the total distance I traveled was 8 meters. We would say my displacement is 8 meters to the right, or we could just simply write positive 8 meters, or even 8 meters east. And we would also say our position is 8 meters, okay, or plus 8 meters. Now let's say, for example, I started at 0, I go to the house, and then I go all the way back here to -2. So we would say my distance I traveled is 8 meters this way, and then another 10 meters this way, which means my distance is 18 meters. My displacement, however, is based on how far from where I started. So I started right here at 0, so I'm 2 meters to the left, or negative 2 meters, or 2 meters west of where I started. That would be my displacement. My position would also be negative 2 meters, or 2 meters west. Now, if you notice, position and displacement are often the same, and in fact, they will always be the same if we start at 0. Let me give you a slightly different example. Let's say we start at our house and we walked 2 meters this way and then 4 meters this way. So the distance I travel would be 2 plus 4. 6 meters would be my distance. My displacement would be 2 meters west, or negative 2 meters, or 2 meters to the left of where I started. My position, however, is always based on the origin. And so my position would be 6 meters east, or plus 6 meters, or 6 meters to the right of the origin. Next, we're going to look at the difference between scalars and vectors. Something is considered a scalar if it has magnitude only, and magnitude simply means the amount or a number. So 5 meters, 1 meter, 2 meters. This would be magnitude or scalars. Vector gives you a little bit more information, and then it also tells you the direction. So 5 meters west, 2 meters east. We could also use simply positive 5 meters or negative 5 meters, where the positive and negative tell you to the right or to the left. So in the previous terms, displacement and distance, which one was the scalar and which one was the vector? Distance was the scalar and displacement is the vector. Remember, when we refer to displacement, we always had to say either to the right or positive or east. These would all mean the same thing, plus 5 meters right, 5 meters to the east. So let's look at a couple other vectors versus scalars, speed and velocity. So speed, we've all heard about speed before, right? Speed is essentially how fast something's traveling. Specifically, this is how far an object travels in a given period of time. So for example, if we're traveling 60 miles per hour, that means that we will, in 1 hour, the car will travel 60 miles. So we're essentially saying how much distance will we travel in a given period of time. Now the standard units, we use miles per hour often, but the standard units are going to be meters for distance, and time we'll be using seconds. So meters per second will be the units. Now velocity is almost exactly the same, except just like displacement versus distance, velocity is going to tell us both speed and direction. So displacement over time. So for example, we wouldn't say 5 meters per second, we would say 5 meters per second east, or 5 meters per second to the west. So we're going to give it a little bit more information, including the direction as well as the magnitude. So the equation would simply be displacement over time. That would be the slight difference. So we'd use displacement over time for velocity. So let's look at an example of the difference between speed and velocity. Let's say, for example, I go velocity, give this guy a velocity of 1 meter per second. Watch the time as he travels. 1 meter per second means every second he's traveling 1 meter. And because it's a +1, it means that he's traveling to the right. Now we would say the speed in this problem is 1 meter per second. We would say the velocity is 1 meter per second to the right, or you could also say to the east. Now notice what happens when I put -1 here. When I put -1, he's now traveling to the left. Now speed would still be 1 meter per second. He's traveling still 1 meter every second here. However, this time, since it's negative, it means he's traveling to the left. Now if I change this to +2, let's go +2 meters per second. Now this one, he's going to travel faster. So notice he's traveling faster. He's now traveling 2 meters every second. And since it's plus 2, he's traveling to the right. If I put negative 5, negative 5 is going to have him go fast to the left. Can I do it quickly? Plus 2, boom. Turn him around. He's now going to the right. Okay, so that's the difference between speed and velocity. Let's look at a few different ways of describing speed and velocity. One way is finding an average. Let's say, for example, I went to Disneyland, which is about 400 miles away. Let's say it took me 8 hours to get there. And I wanted to know what was my average speed. Well, to find that, I would simply say, well, I traveled 400 miles. That's the total distance that I traveled. And it took me 8 hours, right? So we would say the average speed was 400 divided by 8, which would be 50 miles per hour. Okay, now I'm talking about velocity. Remember, you would have to include the direction. So we would say I traveled 50 miles per hour south. So we could therefore define our average as the total distance over total time, or the average velocity is the total displacement over time. Constant speed means that our speed remains the same. So one of the ways I could do this is, well, I could put my car into cruise control at 50 miles per hour, and I would know, well, I would therefore get to Disneyland in exactly 8 hours. And that's if I'm traveling at the same speed the whole time. Now we know in reality we would never do this. Our speed would continually be changing. Maybe we're going 70 at one moment or 60 at another. Maybe we're stopped, right? Well, these different speeds are what we refer to as instantaneous speed. And this just means how fast we're moving at a given instant. And we can easily find this when we're driving by looking down at our speedometer. Okay, so let's look at an example. Let's do one example of this. Here's an example, and for all the problems in this class, whenever I give you an example, the absolute best thing you can do is to push pause and attempt to solve this on your own. So try to answer this by yourself. And if you can do that, really, you're going to solidify your knowledge. You're going to really understand these problems better. And once you've attempted this by yourself, then unpause it and you can watch me solve it, and the parts that you didn't understand hopefully will become clear. So why don't you do that now? Go ahead and push pause, and then we'll come back to this problem. So let's go ahead and solve this one. I would recommend sketching this problem out just to start with. So for example, we have our car first traveling 20 meters east here. Let's call that segment A. And then the car is going to travel 30 meters east here. Let's call that segment B. He's then going to stop, so we'll call that stopping period segment C. And then he's going to come backwards west for 10 meters. Let's write this 30 meters. And then he's going to come back 10 meters. So there's kind of a visual, and we'll call that segment D. Okay, let's go ahead and solve this. So the first one is we're going to look for the distance, right? And distance is, well, how far did we go in total? So we went 20 meters plus 30 meters plus 10 meters. So that's going to be 60 meters. So the total distance that I traveled, the car traveled, was 60 meters. The displacement, on the other hand, is how far you are from where you started. So this guy went 20, 30, and then came back 10. So he's exactly if we started here, he's going to be 40 meters away from where he started. So we're going to just write the displacement here as 40 meters. Let's next find the instantaneous speed. So that means that each of these instants, we're going to be traveling different speeds. So there's really 3 different speeds that we're traveling for A, B, C, and D. So let's go ahead and do A. So segment A, we're going, well, 20 meters in 5 seconds. So that means the instantaneous speed during that time is going to be 4 meters per second. And we're just going to do this for each of the 4 segments. So B, we went 30 meters. and that took us 4 seconds. So that's going to be 7.5 meters per second. Letter C, we're stopped, right? So 0 meters, and it doesn't really matter what the time is, we're moving 0 meters per second. And then letter D, this one we're going 10 meters west, right? So we're now going 10 meters, and this takes us 2 seconds. So that's going to be 5 meters per second. So these would be each of the instantaneous speeds for those segments. Now for velocity, remember, all we're going to do is include the direction. So for this one, we're going 4 meters per second east. Here we're going 7.5 meters per second east. Now when we're stopped, there really isn't a direction, so we don't need to do anything with this. Here we're going to be moving 5 meters per second west. Now remember, you can also use signs, positives and negatives. So we could say instead that this is positive 4, this is positive 7.5, and this is negative 5. Okay? All right, so let's go ahead and find the average. So for the average, we're just going to use total distance over total time. So we'll write S average, and actually the symbol we use for average is a bar. So if you see S bar, that means the average speed. So the total distance that we traveled was 60 meters. And the total time that this took was 5 plus 4 plus 2 plus 2, so that was 13 seconds. So we're going to see for this journey that the average speed was 4.62 meters per second. Now for the V average, this part is a lot of people miss because, well, here we just figured out the direction, right? East, east, west. Here you do not just simply take the same number and do east. Notice velocity is going to be the displacement over time, the total displacement over the total time. And our total displacement in this case was 40 meters. And it still took 13 seconds. So that's going to give us a smaller number, right, mathematically, and that's going to give us 3.08. So one of the big questions is, why is this less? And the direction is still going to be east or positive. So why is this number less than the 4.62? Well, basically, when you're talking about speed, you don't take into account direction. So we just said, oh, we're averaging the 4 and the 7.5 and the 5 meters per second. But when you do velocity, you do take direction into account. So for example, we're going 4 this way, 7.5 this way, and then when we come back, we're traveling a negative velocity. So it's kind of like these two they start to cancel each other out as we're going backwards. And in fact, if we ended up back where we started, so if we started here, we came all the way back to the beginning, our average velocity would actually be 0. Because maybe we have 5 meters per second averaged this way, and then 5 meters per second averaged in this direction, and that would cancel each other out, right? -5 this way to give us a total average of 0. Okay? So the last major topic we're going to look at is acceleration. And acceleration is essentially how quickly your velocity is changing, or the rate of change in your velocity. Now, when we think of this, there's 3 ways this can happen. The most common way is, when you think about it, is probably speeding up. So if my car begins to accelerate, it gets faster, right? This also can be slowing down. So if I'm traveling at a certain speed, I hit the brakes, I'm slowing down, we would say there's also an acceleration. Sometimes we use the word deceleration in that instance. The last way is a less common way of thinking about it, but it still is an acceleration, is when you change direction. So if you have a car traveling and it turns a corner, that would be also, there has to be an acceleration. And the reason for this is, remember, the definition is how quickly the velocity is changing. So if I'm going north and then going east, even if my speed is staying the same, my direction is changing. I'm now going north and now I'm going east, and therefore there must be an acceleration in that instance. The equation for acceleration is essentially as the definition, so it's how quickly the velocity is changing. So we could write this as change in velocity over time, or delta v over t. The units for this, well, if you notice the units for velocity are meters per second, and the units for time are seconds. So the units for this would be meters per second over second, meters per second per second. And we oftentimes write this as meters per second squared, just to simplify it. But I like to use this terminology because it really helps to explain the concept of what's going on. So let's look at a visual of this. So let's look at this visual. We have our guy over here, and this time I'm going to plug in an acceleration of 2 meters per second. So what that means is every second he's going to start speeding up by 2 meters per second, okay, until he hits the wall. So let's play this back in slow motion. So remember, his acceleration is 2 meters per second, which means, slow this down, which means if we're traveling after 1 second, he should be now traveling at a speed or velocity of 2 meters per second. So 1 second means he's now traveling at a speed of 2 meters per second. And after 2 seconds then, how fast should he be traveling? After 2 seconds, he should be traveling 4 meters per second, right? So he's speeding up here. He went from 2 to 4, and let's see what happens after 3 seconds. After 3 seconds, he's now traveling 6 meters per second. So acceleration, so when we say meters per second, it's how fast his velocity is increasing every second. So after 1 second, it's 2. After 2 seconds, it's 4. After 3 seconds, it's 6 meters per second, and so forth. Let's take a look at the directional meaning of velocity and acceleration. With velocity, it's pretty straightforward. Positive velocity means we're traveling to the right, to the east, and negative velocity means we're traveling to the left or to the west. And with acceleration, it's actually the exact same thing. Positive acceleration means to the right, to the east, and negative means to the left or to the west. Now this is a misconception because a lot of people think positive acceleration means speeding up and negative acceleration means slowing down. And this is not true. To figure out whether it's speeding up or slowing down depends on both the velocity and the acceleration, what each of them are doing. So there's 4 cases here. What I'd like you to do is to go ahead and push pause on the video, write these down, and then I'm going to use the visuals to help explain these in more detail. So push pause now. So let's take a look at a visual of these 4 different cases. The first case is when we have both a positive velocity and a positive acceleration. So let's make both of these +1 and +1. I'm going to show you also the vectors, the arrows showing the direction. So the velocity is going to the right, and the acceleration, the green one, is also going to the right. So notice what's going to happen is the guy's going to keep getting faster and faster and faster, okay, until he hits the end. And this would be a case of speeding up. So we had, this was +1, this was also +1. Let's go ahead and play it back in slow motion one more time. So you can see he's moving faster and faster and faster. And if you look at the red arrow, notice the red arrow keeps getting bigger and bigger because he is increasing in speed. Okay, so this was case number 1. Let's take a look at another case. Let's look at case 2. So let's put him back here at -10. And we're going to give him a velocity this time of +5. And we're going to make his acceleration -1. So what this means is that he's moving fast quickly. And notice he's starting to slow down and slow down and slow down. So he's getting slower and slower and slower, right? Let's play this back in slow motion. So when these are in opposite direction, the guy is slowing down. So we have a positive velocity here and a negative acceleration, and it's causing him to slow down until he eventually reaches 0, right? He's going to stop right there. Let's go ahead and look at case 3. I'm going to put the guy over here at 10 meters. Let's record clear. We're going to put his velocity is going to be negative, so we'll put -1, and his acceleration is also going to be negative. So notice in both these, this last case and this case, his acceleration is negative in both. However, watch what happens. In the previous problem, he was slowing down. In this problem, you can see that he's speeding up. It's getting faster and faster. So this will happen when, well, when you're moving, when the velocity and the acceleration are in the same direction. This tells you that he's going to be accelerating. So he's going to be speeding up. So he's moving faster and faster in this case. Okay, last case, this is the one that people usually have the biggest trouble with. So we're going to put him back at -10, actually +10. We're going to make his velocity a -5, -5, and then let's make his acceleration a +1 this time. So why don't you predict what's going to happen? Okay, so his velocity is to the left, and his acceleration is to the right. So notice what happens. Well, he slows down. Okay, if we play this back, slow motion. So when they're in opposite directions, when his velocity is to the left and acceleration is to the right, his acceleration is positive here, but it's causing the guy to slow down, and he's getting slower and slower until he eventually stops. Actually, let's run this one more time. But this time, let's just let it keep going. So we'll start with 5, -5. Oops, pause, clear. So let's give him a velocity of -5, and then let's give him an acceleration of +1. And I'm just going to keep this running instead of stopping it. So notice the acceleration is +1 the whole time. And his motion, his velocity is clearly changing here. So in this case, since we started at a negative velocity to the left, the positive acceleration is causing him to slow down. He's getting slower and slower, and eventually he's actually stopping. Notice in this case, the acceleration is not changed. It's still +1. And in fact, what it's doing is it's changing its direction. He's going to the left, and then at that one instant when he stops, he then turns and starts to move towards the right. And so now he's going to be accelerating, speeding up in this case, to the right. So remember, what's going to happen with speeding up or slowing down is dependent on both the acceleration and the velocity. A big misconception is that negative acceleration means slowing down. However, as you can see in these examples, sometimes it means slowing down, sometimes it means speeding up. Okay, all right, so that ends the lesson for today. In the next lesson, we will be taking a look at more of the mathematics of the acceleration and get into a little bit of that. So I hope this video is helpful. Please let me know if you have any questions.